Okay, so here's where I'm going to review a few of the questions from that RLC assignment, and that way demonstrate the process and show you how to solve them. And then after that, the next thing I'll do is I'll be going through the power presentation as our final presentation for this course, and I should have that published tomorrow as a YouTube video. And then we'll be able to do all of the questions involving AC power. Okay, so the first question that I'm going to look at is question number 2. I do have the solutions shown on D2L, and I think question number 1 is pretty straightforward, so I'm not going to bring that one up. But question 2 is one I'm just going to start with as a simple question, but one that we'll cover in full detail. So if I read the question, it says a practical coil with a resistance of 50 ohms allows a current of 0.5 amps when 220 volt 60 hertz supply is connected across it. It wants us to draw an impedance triangle, determine the reactance or the XL of the coil, and its value of L in henries. So let's start by first of all drawing the diagram of the circuit, which is an AC source of 220 volts, 60 hertz, and we're connected to a practical coil. And if you remember, when we're talking about a practical coil, the model we use to represent a practical coil is an R value of R coil in series with an L value for an inductor, right? So here's our L value. So when we're modeling that, we show a series connection. That means that our total impedance, Z coil, would be equal to R coil plus J XL. That would be our total impedance. That also could be represented as Z total at angle phi or phi, right? Or Z coil at angle phi or phi. So when we're looking here, we're also finding that we've got an I here of 0.5 amps and a R coil value of 50 ohms. Now, we haven't been given a value of L, because that's one of the things where you need to determine. We haven't been given a value of XL either. So based on that, we can use our impedance triangle in order to determine that missing value of XL or L. So an impedance triangle for a practical coil, of course, is going to involve that plus J component of XL, that R component for R coil, and then of course here is going to be our Z coil as the total impedance of that inductor. So we know this is equal to 50 ohms as per our diagram. We don't have this and we don't have that, but we can come up with this based on the fact that we have current. So that means that Z coil is going to equal V coil divided by I coil. So when we look at this being our coil, we know that across that coil we have a total of 220 volts. So 220 volts and divided by a 0.5 amp current is going to allow us to calculate our value of Z coil, because remember, when it comes to the impedance of any component and or circuit, if we have the applied voltage and the total current, dividing the current into the voltage is going to give us that total impedance. So that means our Z coil impedance here then is one that's made up of R coil plus XL to give us that value. So in this case, that would be 440 ohms. So now if we just add that to our diagram, 440 ohms, we can come up with a XL value. Now, XL then is going to equal the square root of Z coil squared minus R coil squared. So if we run that through our calculator, I've got a value of 437.15 ohms. So XL then means that's equal to 437.15 ohms. So we drew an impedance triangle, and now we're going to put XL in here. That's 437.15 ohms. So now we have a complete impedance triangle indicating R, XL, and total Z. And then what it wants to do is determine the XL value, of which we got, and lastly we can get the L. Right? So if we're going to determine the L value, L is going to equal XL over 2 pi F. And so that's going to be 437.15 over 377 for the angular velocity of 60 hertz. And if you work that out, it comes out to 1.16 henries. 1.16 henries. So that's the way you do question number 2. A couple of things to just remember is when you have a applied voltage and a current, you're always going to know the impedance of a circuit by using Ohm's law. That will be your total impedance. The other thing is when you have an impedance triangle with the hypotenuse and one of the sides, then you can just use essentially Pythagoreans here to come up with the missing side, or trigonometry if you choose. And yeah, that should, I think, cover question number 2. Okay, so next one I'm going to look at is question 4 from that assignment now. So if we look at question 4, I put the schematic diagram up here already and labeled the values. R1, 10 ohms. We're given an XL value of 15 ohms. So for the coil, I've indicated its reactance of 15 ohms. And then over here in branch 2, we have R2 of 20 ohms and a C value of 220 microfarads. So we've been given a value of capacitance there, of which we'll have to use with the frequency in order to determine its reactance or its opposition. So once we start working on branch 2, we'll have to address that. Now, I just want to remind you guys once again, in any problem where you're not given the frequency, like we are here, don't forget you're to assume 60 hertz and move forward with 60 hertz. So that means if this wasn't given, you wouldn't have to ask, because you'd assume 60 hertz and an angular velocity of 377. All right. So that being said, then let's talk about our approach here. This is of course, a series parallel AC circuit where you have 2 independent branches, right? Branch 1 operates independently of branch 2. You know that's a property of a parallel connection. So what we're going to do is we're going to treat them as 2 separate circuits for our analysis, and we'll start with branch 1. So I'm going to put branch number 1 up here. When we look at what we're asked to calculate or determine for this question, we've got I total as our total current in the circuit, I1, I2, branch 1's current, branch 2's current. It indicates that we want to use our E source, or our source voltage, as a reference, which is very common in power systems, like I said. And then within each one of these branches, we're going to have a voltage triangle, because it's a series arrangement, right? So each one of these impedance triangles that comes from this impedance is going to develop a voltage triangle for branch 1 and branch 2. So what we'll do is we'll determine the voltage drops for VL and VR1 in branch 1 but we'll use I1 as the reference. And then for the second branch, we'll determine BC and VR2, or VR2, and we'll use I2 as the reference. Lastly, we can do a simple calculation using Ohm's law to determine Z total. Okay. Now, branch 1 then, if we look at the impedance of branch 1 could be Z1 is expressed as 10 ohms plus J 15 ohms. That would be our rectangular expression for the impedance of branch 1. I'm going to use polar to do these calculations, so if I convert that to a polar value, that means that my branch 1 impedance works out to 18 ohms at 56 degrees. So I'm going to use that for my calculation based on a polar value. Of course, you could move forward with this as rectangular. I'm going to show this solution as using polar. So that means, oh, and I'm sorry, I didn't include my negative angle in there. When it comes to phase angles, you don't need to include polarity. Calling this 56 degrees and calling this also a positive value is not incorrect, but in my analysis, I always include this polarity because I think it helps sort things out when it comes to identifying by your calculation whether it's inductive or capacitive. If you just called this 56 degrees, somewhere along the line you'd have to indicate that it was inductive, so you'd understand that it was a lagging current when you were doing any kind of further analysis. So in my case, I just put minus 56 degrees in there to indicate that sorry, that should be a plus 56 degrees. Okay, well, this may end up on the blooper reel instead of solutions here, but yeah, sorry, the impedance is plus 56 because we have a plus J component. I'm sorry, I have to now indicate the I1 value, which will be our source voltage, E source, at 0 degrees. And remember, we were using E source as our reference, so I've got E source at 0 degrees divided by that impedance, Z, at angle phi or phi. So in this case, we have 100 volts at 0 degrees divided by our impedance, which is 18 ohms at 56 degrees, to give us a current, which is going to be lagging, of course. We're going to have a minus or a lagging current here. So if I look at that calculation, I got 5.56 amps at an angle opposite to our impedance. And this is where what I meant to say was I include that angle as minus 56. Now, we know this is an inductive branch, so Eli would have to apply to that branch. And sure enough, we can see that our current is lagging our voltage by 56 degrees for that example. So we've really determined our current already with respect to our applied voltage for I1 right here. Okay, now let's move on to branch 2. Branch 2, following that same procedure. First of all, we have to figure out our XC value. And our XC value, I have it written down, so let's just calculate XC now. So we know that's going to be 1 divided by times 2 to the 1 exponent minus 6. Works out to 12 ohms. So let's put that in here. XC equals 12 ohms. So if we look at our impedance, we could draw a triangle and represent it that way using the rectangular values. In this case, I'll just indicate that our Z2 series impedance, one that can come directly from adding those values together because it's in series, would be 20 ohms plus minus J, 12 ohms. Okay, we have minus J for XC. So now, if we look at converting that to a polar value, I can see that that equals 23.3 ohms at an angle of 31 degrees, or minus 31 degrees. Yeah, minus 31 degrees. Again, because it's a minus J component, it's going to be minus 31 degrees. So here we have a lagging impedance, or an angle phi of minus 31 degrees. What we can do now to determine I2 is we can say E source, same source voltage across that parallel branch, at 0 degrees divided by Z2 at angle phi. So that's going to be 100 volts at 0 degrees divided by 23.3 ohms at minus 31 degrees. Okay, the result should be a leading current because it's a capacitive branch. And you have 4.3 amps, 4.3 amps at 31 degrees. So that means that the current in this branch is leading the applied voltage, as we know it should be, using this acronym for a capacitive branch. We know that it's leading, as indicated here, it's leading the applied voltage with E source as reference at 31 degrees. Okay, I'm going to pause it here, erase this, and we'll move on. But now we've got our branch 1 impedance and the current, our branch 2 impedance and the current. We'll move on to the next step. All right, so we're back to this, and we've already come up with I1 branch 1's current and I2 branch 2's current. The next thing we can do is we can come up with I total, right? Now, remember, both of these currents we calculated with E source as the reference. So because they've got E source as the reference, if we simply just add the two of them together as a polar value, we'll end up with an I total value with respect to E source, and that's what we want to do. So that means that our I total value is going to equal I1 plus I2. So if we take our I1 value as a polar value, we had 5.56 amps at an angle of minus 56 degrees, the lagging current from the inductive branch, added on to the leading current of the capacitive branch, 4.3 amps at an angle of 31 degrees. And put that in your calculator, you'll come up with 7.2 amps at an angle of minus 19.4 degrees. Okay, so that means now we have I total with respect to the source voltage that we were looking for right there. Now, thing is if we have I total, we can get Z total for any circuit, can't we? Because that'll be Z total equals E source at 0 degrees divided by our I total value at angle theta. Okay. Now, something to be aware of. Notice how in this question it asks for Z total, but it doesn't ask for an angle of impedance, because it's really not necessary when we've got these other angles like our phase angle right here from this total current. So I want you to be aware of that. If a question does not ask you to express a angle with respect to some reference, it's just looking for a quantity. So really here, when we're asking for Z total and we didn't ask for an angle of impedance, we're just looking for a quantity. So I just wanted to make sure that's understood. So that means all we really need to do is do 100 volts divided by 7.2 amps. And that's going to give us our impedance, and that's going to be 13.88 ohms of Z total. Okay? All right, so again, running out of board space here, so I think it's best that I pause, erase this, and then we'll come back to solving these voltages, right? Because we've got our currents, we've got our impedance, now we just need to do our voltage triangle, if you will, or our voltage drops in each one of these branches. Okay, now we're going to do our voltage drops in branch 1. We know, based on Kirchhoff's voltage law, that our voltage drops should be VR and VL adding up to E source, right? So once we calculate these values as a rectangular value, if we did a rectangular to polar conversion, of course that should equal an E source value equal to 100 volts. So let's come up with our value of, now remember this is all with I1 as the reference, so I1 will be set at 0 degrees. So that means we can multiply 10 ohms at 0 degrees for our impedance of the resistor times our I1 current, which was 5.56 amps, and we're going to have 0 degrees because of the reference there, and of course this voltage is going to be right in phase with I1, and so that's going to be 55.6 volts at an angle of 0 degrees with respect to that current. It's a resistor voltage, so it's going to be in phase with that branch current. Then we'll move on to the next one. The VL value is going to be our current, same current, right, multiplied by our XL value. And our XL value was 15 ohms, right? So then we're going to have 15 ohms at 90 degrees, right? Because that's the plus J component of XL times 5.56 amps at 0 degrees for our reference. And then we're going to get 83.4 volts at an angle of 90 degrees. So that means in our triangle here, we've got 55.6 volts for VR, 83.4 volts for VL. Our E source value then, as a rectangular value, would be 55.6 volts plus J, 83.4 volts. And I guarantee if you were to put that in your calculator and do a polar conversion, you would end up with your ES value at a value that's equal to the angle of that current, because we've got the current as the reference now. So this would be an angle of 56 degrees once you figure that out, right? So that would equal 100 volts at 56 degrees. And why would it be 56? Because our I1 current here is our reference for that triangle. Okay, so I'll erase this once again, and we'll go. Well, I can just do that right now. Let's go into our branch 2 voltage triangle, right? Because now we've covered this one, the V drops of branch 1. Now we'll do the branch 2, and we've got VR2 is going to equal our I2 at 0 degrees times our R value, right? So our I2 value was 4.3 amps. That's going to be 0 degrees, right? Because we're going to use that as a reference. And we're going to multiply by 20 ohms at 0 degrees, and that's going to give us 83.4. No, 86. Yeah, sorry. 86 volts at 0 degrees, because it's a resistive component. It's going to be right in phase with that I2 current. Now we move on to VC. VC is going to be our 4.3 amps at 0 degrees as a reference, but we're going to have to multiply that by our XC value, which we know is 12 ohms at minus 90 degrees. Right? So at minus 90 degrees, we're going to have a 51.6 volts at minus 90 degrees. So that minus 90 degrees is our, with reference to the to current. And you know that based on that, we're going to have a voltage triangle like this. VR, VC. This should equal E source, because remember it's a branch right across the source. VR equals 86 volts, and VC equals 51.6 volts. And if you were to indicate that as an E source value, it would be 51.6 volts plus minus J, 86 volts plus a minus J, 51.6 volts, of which if you do a polar conversion on that, you would get E source equals 100 volts at your angle here, right? Because this is with respect to that current, right? So the source voltage with respect to that current is going to be a lagging angle of a minus angle, and that would be minus 31 degrees, because that was our angle, or phase angle for that last branch. Okay, so that should be everything for question number 4.